right, today we get to look at natural log integration. So just a reminder, this is kind of the general rule for natural logs. If I have the integral of 1 over x, that comes out as ln of x. I do need the absolute values here, and the reason that I need the absolute values is because 1 over x contains a negative portion and a positive portion. So I want to be able to do the x value of either of those portions. Without that absolute value sign there, it will not let me take the natural log of this negative portion if I need to find the area over there or something like that. And then we got plus c since we are doing indefinite integrals. So first one should be pretty straightforward. You can factor out the 10 if you want to, but this would just be 10 ln of x plus c, right? We had stuff like that in, what was that, 5.3 homework, 5.2 homework? I can't remember. Okay, stuff like this. This isn't just 1 over x or a number over x or something like that. So if it helps you, do use substitution, and then that would mean that du is just negative 4 dx. So du over negative 4 is dx. And if I make that substitution and I pull out my 9, this is negative 9/4, the integral of 1 over u du. So I have negative 9/4 ln absolute value of u plus c. So this is negative 9/4 ln absolute value 5 minus 4x plus c. That would be my final answer. All right, this next one, it's a little bit tricky to see at first, but it looks pretty ugly. However, I have higher exponents in my denominator than my numerator, so what I would try to do, and just see what happens, is let u equal my entire denominator. So x cubed plus 6x squared plus 5. So then du would be 3x squared plus 12x dx. And what I notice is the cool thing here is that x squared plus 4x is kind of trapped in here, right? It's just multiplied by 3. So if I factor out that 3 and divide it over, then 1/3 du is x squared plus 4x dx. So I can change all of this junk into 1/3 the integral of 1 over u du. Oh yeah! So 1/3 natural log of u, which would be x cubed plus 6x squared plus 5, absolute value, plus c. That would be my final answer there. All right, this one is going to take some remembering. I have a higher exponent in my numerator than my denominator. So it would be nice, right, if this was just an x or something like that, because then I could just rewrite this, divide that x out of my terms that I can. But it's not just an x, it's an x minus 2, but still we can apply the same logic. We can divide out that x minus 2 using synthetic division. So if I set up synthetic division, I'd have 2, 7, negative 3. Then I pull down the 2, 4, 11, 22, 19. That 19 is my remainder. So what I can make this become is the integral of 2x plus 11 plus 19 over x minus 2 dx, right? That is what this part is. This part is 2x plus 11 plus 19 over my divisor. So now this becomes a lot easier because really this is the integral, if I split this up, 2x plus 11 dx plus 19 integral of 1 over x minus 2 dx. And if I do use substitution, like if I let u be this, then du would just be 1 dx. So in my head I'm thinking, well, u is x minus 2. So if I do the antiderivative here, this is x squared plus 11x plus 19 ln absolute value of x minus 2 plus c. That would be my answer for this one. Okay, here, I think we did something like this before, I can't remember, at least with u substitution. So if I let u equal ln of x down there. And I do that because I noticed that du would be my 1 over x dx. So du is this part, and then u is right there. So this comes out as 1 over u to the third du, which if I do the antiderivative of that, maybe it'll help you if I rewrite this, u to the negative 3 du, because it would be u to the negative 2 divided by negative 2 plus c. So I would rewrite this as negative 1 over 2 ln of x squared plus c. Alrighty. Tangent of 5 theta d theta. We do not know the antiderivative for tangent, but now we will. Because what you can do is you can make tangent sine over cosine, as long as you're keeping the angle the same. And I am going to let u equal my denominator here, such that du would be negative sine of 5 theta times 5 d theta. Oop. All right. So now I have the sine of 5 theta, but I don't have the negative 5, so I'm going to divide that over. So negative 1/5 du is sine of 5 theta d theta. So I have negative 1/5, the integral of 1 over u du. So this is negative 1/5 ln of u, which u is cosine of 5 theta, plus c. Alrighty. Okay, find the particular solution of the differential equation. So what I would do is I would do a separation of variable here first, and I would multiply up that dx. So dy equals x minus 2 over x dx, such that now I can take the integral of both sides, such that this is y plus some constant 1. And over here, I would need to rewrite this, right? I would do x over x, so this is really the integral of 1 minus 2 over x dx. You guys kind of see what I did. I'm dividing x by x, which gives me 1, and negative 2 over x is just negative 2 over x. So that's kind of like what we wanted to do before, except we couldn't, so we had to do the synthetic division. So this would be x minus 2 ln of x plus some other constant 2. I would combine those constants. So x minus 2 ln absolute value of x plus whatever constant it is. Then I need to think about my solution. So I have 0 equals negative 1 minus 2 ln absolute value of negative 1 plus c. Well, ln of 1 is just 0, so I lose this term to 0. So that would mean that c equals 1. So my particular solution would be x minus 2 ln absolute value of x plus 1. Alrighty. Find the area of the region bounded by the equations. So let's see what we have. We have 5x over x squared plus 2. That'll be easy enough to do u substitution with. From 1 to 5, so if you're thinking about the graph of this thing, let's see, y equals 0, 5x, x squared, it's going to be positive, so something-ish like this, right? And I'm just trying to find the area from 1 to 5, and between y equals 0 as well. Right, so it's just bounding it by the x-axis. So I would set this up as the integral from 1 to 5 of 5x over x squared plus 2 dx. That is what I'm trying to evaluate here. And notice it says area, so I will use unit squared in this case to answer my question. Okay, so I would do u substitution. I'm going to move this over. And I would let u be my whole denominator there. So that du is 2x dx. All right, so I don't have a 2 So what I would do is I would make this 1/2 du equals x dx, and I would factor out that 5 in the first one as well, in the first, can't talk, first integrand. So this would be 5/2, 1, 5, x dx is du, so I have 1 over u du, but I did a no-no. Take a second, if you think about my no-no. My no-no, no, is my bounds. I need to change my bounds because I'm no longer integrating in terms of x, I'm integrating in terms of u, which also means I don't need to change them back. So again, your two options here are to either leave your bounds off or to rewrite your bounds in terms of u. I prefer to rewrite them in terms of u because that usually makes calculating stuff a little bit easier because I don't have to change them back. So what I mean by that, right? If x is 1, that was my lower bound. If I throw in 1 to my relationship, then I'm starting at 3 for u. And if I throw in 5, choo-poo, that would be from 3 to 27 of 1 over u. Now when I do my integrand, I have 5/2 times the antiderivative of this, which would be ln of u, from 3 to 27. Right, the nice thing is I don't have to turn it back into terms of x, so I can just make this 5/2 of ln of 27 minus ln of 3. Both of those are positive, so I'm not going to worry about the absolutes. And don't forget your properties of logs. They would probably write this answer as ln of 9. Right, because don't forget ln of a minus ln of b can turn into ln of a over b. Means the same thing. So 27 divided by 3 is 9. That would be my area in units squared. Oh yeah. Okay. Now this next one is one that you will probably need to memorize. These next two really, this one's pretty obvious down here, but these next two, you could for sure see them, and the proof to get here takes a little bit of finagling. So I'm going to show that the integral here is equal to the natural log of all this junk. So taking this integrand, I'm going to make it 1 over cosine of dx. No, I'm not. I'm lying. I am just kidding. I do not want to do that. What are you thinking, Mr. Pike? So, what I really want to do is I am going to do something crazy, and I'm going to multiply by secant plus tangent. And you're thinking, why in the heck would he do that? And I am too. Because it's something that they were trying to find the integral of this thing, but it was very difficult to do. However, they realized with natural log integration and logarithmic integration, the top here would turn into secant squared plus secant tangent. And my denominator is just secant of x plus tangent of x. Cool thing now is I can let u equal secant of x plus tangent of x, and if I take du, well, hey-oh, derivative of secant is secant tangent, and the derivative of tangent is secant squared dx. Is that not what we have right there? So this comes out as the integrand of 1 over u du, which I know is just ln of u plus c, which then is ln of secant of x plus tangent of x plus c. Oh yeah, big money, right? And that shows that that is equal to that. That's the trick they needed to pull, right? Because when I rewrote this as 1 over cosine, if I try to let u be cosine or something like that, it won't work out because du would be negative sine of x dx. So there's just not anything really great that we can do, so we kind of have to finagle it a little bit, which is essentially the same sort of idea I'm going to do on this one, except it's with cosecant cotangent. So same idea, if I take that cosecant and I multiply this junk by cosecant of x plus cotangent of x, dx, and I let u be the denominator, then du is negative cosecant cotangent minus cosecant squared dx. So now we're really close, except for that is a positive in my numerator, right? This will be cosecant squared plus cosecant cotangent. Well, that's close, but it's just negative. So all I need to do is say, well, hey, then negative du is equal to that stuff. So this becomes the negative integrand of 1 over u du, which is then negative ln of my u, which was cosecant of x plus cotangent of x, plus c, since I am an indefinite integral there. Right? And that will show that that integral becomes that. It's probably easier just to memorize these than it is to show them and think about that trick each time, but this is an integral that's going to be fair game. You'll start seeing it on quizzes and tests for sure. Okay, this next one is pretty straightforward. You probably don't need to memorize this one, and the reason being, same reason that we did for tangent earlier, is if I make this cosine over sine, and I let u equal sine, then du is cosine, and so that I can say that this is the integrand of 1 over u du. So pretty straightforward, ln absolute value of sine plus c. Okay. All right, hopefully this video was helpful. If you guys have any questions as you are going through your notes, going through your homework, whatever, please reach out. I am here for you, and I will talk to you all soon.